Hello, everyone. The topic of this presentation is the beauty of big data privacy engineering. My name is Yangchen Huang. I'm a director of software engineering with Strata. So before we move to the presentation, please allow me to do a quick introduction about Strata. Strata was a startup founded in 2018 by Mastercard and IBM. Strata is specialized in data privacy. So we're basically offering this data anonymization solutions and services for different companies across different industries. With data processing platform like Spark, it's not so difficult to remove privacy information or any sensitive information from a big data set. But what Strata is specialized in is we can balance the trade-off between data privacy and the data utility. That's what we are good at. So basically, we provide a number of consulting services, but also our big data platform to a number of different clients across different industries. We actually heavily use Spark in our data anonymization and data analytics platform. So the problem I want to discuss here is actually one of the very important challenge in data privacy. It's called geo-privacy. In nowadays, everyone uses so frequently with a mobile phone, so our GPS information is actually shared and used by a number of companies, no matter you know it or not, day in and day out. So if you go online, if you search the geo-privacy, you will find a number of interesting news how people's privacy is actually was intruded by different kind of GPS information leak. So this particular problem, we try to generalize the customer's GPS the customer's GPS information and into a postcode level information, so that in a postcode level, so there will be multiple customers in the same postcode, so that each person is not isolated based on their location information. So the input of the problem essentially is a large data set. It's a more than 30 million of customers' GPS location information, and also the zip code information. The zip code information is basically each zip code is actually a shapefile. Each shapefile, if you have experience with geometry processing, basically each shapefile essentially is a shape, including a number of points. Each point is actually a GPS point. So with these two input, we try to mapping each customer's GPS location information onto a zip code, so that at the final data set we send for anything like advertising will be only on the zip code level. Based on this, we need to further to calculate between the zip code. We try to calculate the nearest 10 zip code, so that we can infer people's shopping behavior. So, for example, if we want to infer the shopping behavior of Ballymoss Road, where Strata is located in, we potentially look at the surrounding nearest 10 zip code. So that's basically the problem we try to solve here. Basically, the first thing we need to do a mapping. The second thing we need to do to calculate the nearest 10. So if you look at the problem here, is essentially a trillion problem. It's basically million by million. So if you want to search, so basically we have 30 million customers GPS information. You have to potentially search 1.7 million British zip code, so that we can do the mapping. So if you look at what Google is processing, like they are doing 60 million web pages per day, 60 billion web pages per day, and doubling population is 1.2 million. So it's just like measuring the similarity of any two doubling people. So this is the complexity of the problem we are facing. The topic of this presentation is called, the beauty of such a big data privacy engineering. Beauty is defined as, the quality in person of the thing that gives the pleasure, make people happy, something impressive and something good. So we can start showing people showing the result of our showing you our processing result. So our customer started the journey using, for example, 200 of processing node. They started to using, for example, Hive SQL, using a library from ESRI, a Hadoop spatial framework. If you Google it, you can easily find it. So our customer use such a 200 nodes. They basically use Hive SQL. They basically try to do a mapping for 5 million customers onto this 1.7 million UK postcode. It actually takes 33 hours to run the job. I mean, when Trata got this task, we basically start with a number of existing libraries, including use Spark SQL. Frankly, we actually use, for example, GeoMesa. We use GeoSpark and a number of different geospatial this kind of Spark library to do this mapping on 8 million, roughly 8 million customers. To map this 8 million customers' GPS information onto 1.7 million postcode. Actually, the job runs 12 hours, still not finished. So I just killed it because, go beyond 12 hours is not acceptable in our SLA requirement. And basically, the team takes the job. Basically, we began to look at the problem. We basically rewriting the whole stuff in Spark Scala with tuning the performance. Actually, at the end of the day, we can map 32 million subscribers onto a 1.7 million postcode within 8 minutes. So basically, in the following slides, I'm going to show you in particular more details of this work from two aspects. One is the algorithm we used. The second one is the journey we have gone through. But the result shows here is quite impressive. We got, for the mapping, we get 1,500 times improvement. For the nearest 10 calculation I just mentioned, the customer started with 200 nodes, but actually the time is the job is never finished. But Spark, when we use Spark SQL, we can finish it initially within 13 hours. And after we tuning the performance with proper spatial indexing algorithm I'm going to introduce right now, we can actually finish it in 1 hour and 10 minutes. So it's 11 minutes, 11 times improvements. So now I'm going to introduce the algorithm and some implementation details of the algorithm. Essentially we use R-tree as the fundamental algorithm to do this spatial indexing. R-tree is like a B tree. It's a tree structure used for spatial access, spatial indexing. It's used to index multi-dimensional information, such as GPS information, rectangles, polygons. The key idea of the R-tree is to grouping the nearby objects and represent them into a bounding box. If you think about the problem we are facing just now, we try to mapping the people's GPS information onto a zip code. So we are searching, this kind of match between GPS and the zip code. Essentially, if the people is in South London, there's no way I should go to Glasgow or Edinburgh to do this search. So I just need to search the postcode in London, right? So that's basically the usability, why we use R-tree, because it provides this bounding box, and so basically the search can be done in each smaller bounding box. You just need to search locally rather than to search in the whole space of the zip code. But a problem of R-tree is the loading time, right? So that people call it the packing time. In this particular solution, we actually use the sort tile recursive algorithm to speed up the loading. How it works is basically like what it shows here in the bottom part of this slide. They started basically to look at the whole geospace. Basically, they look at the maximum boundaries of the whole geospace we are looking at. Then after we have the maximum boundary, it began to do a partition. That's where this sort tile recursive function comes in. It's basically try to partition the geospace into smaller ones until it reaches a certain level. The smallest box curtains only at most, for example, 9 points in this example. So it is widely used, but this is possibly the first time actually we saw it used to do this our particular problem. For example, there are a lot of other libraries like GeoMesa, like GeoSpark. They have been using this kind of to do spatial analysis, but their focus is mainly on a query-based. For example, if I have one GPS, I want to do a query to do some spatial analysis on this GPS data point. So that's basically existing algorithm is focused on. But what we are doing is we basically try to mapping a bunch of customers' GPS information. It's 32 million of GPS point onto another nearly 2 million kind of postcode locations. So this kind of batch processing at this volume is quite new. So, and the journey we have gone through is actually another part we want to introduce here. It's a combination of 99% of partition plus 1% of scales. The algorithm we just introduced there. The story starts with the customer run with if based on the customer runtime, it's potentially a few hundreds of hours of and required to really run this the geomapping function. We took it, we ran with Spark SQL, and we actually it's never finished here. So, but by looking at the nature of the problem, look at the logic, you make full use of this locality. The geolocality is actually quite essential. This is basically we can shrink the problem into a smaller scale and to solve the problem by applying this R-tree onto data frames, onto data RDD. We quickly can achieve the mapping in 4 minutes. It seems everyone is happy. It's a wow factor, and the story seems to end there. But actually, in reality, it's not, because we need to move this piece of information. Move this algorithm into production. What does this mean? Move a analytics or geospatial algorithm to production means we start to introduce something like data pre-processing, right? So we need to pre-process data. We need to really output the data into proper format. But then we found our algorithm actually increased from the runtime from 4 minutes increased to 10 minutes. It's still acceptable, right? It's 10 minutes. But then we began to look at the end-to-end problem, right? We need to bring in more customer information. In addition to the GPS information we have, we also need to have other customer-related information so that from the customers, so that we can build an end-to-end solution. After we introduce, all this transactional information of the customer into this picture, we basically introduce a few joins, together with the postcode information, the geometry and the postcode string, this kind of mapping. Quite a number of joins is added into the picture, and then we found actually our running time increased sharply to 5 hours. This is expected or not expected. That's basically what each big data engineer is facing. But a lot of people actually stop there and begin to, this is as good as we can. But our team is not stopping there. We keep look at the problem, and we believe there should be a better achievement, a better result, rather than just stay with five hours. So we began to extensively tuning the parameters to a greatly, optimizing the performance. Actually, we found not too much improvements. And then after we look at the partitioner and the distribution of the data set, we found, wow, the reason is quite classical. It's basically after we do a few joins, the data distribution of originally well-distributed data set is already distorted. It's a typical data skewness we are facing, and we begin to look at how data essentially we begin to look at the lineage of the data distribution. How data distribution has been changed before and after each join. So by looking in depth into the problem, basically we began to think about we need to rewrite the transmissions. For each transmission, we basically remove all these unnecessary transmissions. If we can use a subset of the Spark data frame, we directly use a subset rather than do more joins. Basically, we remove unnecessary joins, remove unnecessary transformations, and we actually put the runtime back to roughly 14 minutes. So it's end-to-end, which is back to that kind of previous 10 minutes around the situation. And after we further optimize the code using in our previous code, we still use some Spark SQL. Not all of them, but there's still some Spark SQL there. We further optimize that part. We actually achieved the end-to-end run roughly at 8 seconds. No, that's basically a typical journey of our big data privacy engineering. I mean, the algorithm is essential to achieve this target, but that's in my view, that's just the start of the whole journey. We basically just use our knowledge on Spark and keep optimizing, not just but we already start with parameter optimizing. Then we begin to repartition the data, do a partitioning, create our own partitioner. All this journey, if it's not working, final state, we begin to really rewriting some of the logic. We found that that's actually a good way of doing privacy of big data engineering in our day-to-day life. So that's potentially every big data engineer has been experiencing from their day-to-day life. It's not just one particular algorithm will lead to a huge improvement on the performance. It's basically the combination of a good algorithm, and then we keep working on the algorithm, keep improving the solutions, and achieve the final target in our production. So, and also it's good to mention that the Spark version we were using when we're doing this work is actually it's 2.0, 2.0.2. It's not like today we have 3.0. Actually, I'm aware there are quite some optimization on data skewness. So all this kind of stuff will make the work much easier today. But the journey we have done here basically give us a lot of experience how we optimize the performance of the work. So this kind of journey is exactly this craftsmanship spirit here, how things plays here. Just like the gentleman what the gentleman is doing on a hardware workshop, we actually working on Spark in similar way. We basically keep tweaking and tuning our performance, our tools, our platforms in such a way that we gradually make some near perfect situations in our day-to-day product and day-to-day solutions. So that's basically our journey. I should say one of the kind of type of journey of this big data privacy engineering. In the slides, basically introduced the first geo-anonymization and geospatial analytics workload with Spark using this R-tree algorithm to maximize the performance, and do this in-memory computation, which achieved a very good result. But also, I showed the journey of production such a workload and such a solution. It's basically the craftsmanship spirit. It's really playing the key role here by keep refining the work and refining the solutions. So far, the work presented here is mainly about GPS information kind of anonymization. So we basically generalize the GPS information onto a zip code level. It's a typical way of doing anonymization called generalization. But in addition to this GPS information anonymization, we do have some other bigger challenges. For example, even each GPS information is anonymized. The sequence of this GPS information, that is the sequence even of the zip code, is still a challenge. There are a number of good papers published on this field. Basically, the trajectory, even each GPS information is anonymized. It's still, the people can still identify a person's mobility based on the trajectory, the sequence of the zip code, the sequence of the zip code or sequence of the GPS information. So we actually published some patent in this field. Another ongoing work is, if for each trajectory, the trajectory can be combined together and build a mobility pattern. How we can anonymize this mobility pattern? That's another kind of work is ongoing. We try to make it a production and build a whole set of solutions for this geo-privacy solution. So we try to publish this as a generic library, which can be used and in more in large scales, and also in more generic situations. That's basically the main part of my presentation today. If you have any questions, here's my contact. Thank you for your attention. Any questions, feel free to give me a shout. Thank you.